So hello everyone, welcome back. Okay, so in this video we'll take up more problems from the sample paper. Before that, some of you had a doubt regarding applying the average magnetic field result for the circular loop. That we discussed in the last video. Okay, so the idea is pretty simple. So whatever the shape of the loop, let's just take an arbitrary loop. Its shape can be anything. So how would we find the flux through this loop? So that would be just the area integral of B dot dA, right? Now the magnetic field here is going to be some constant K times X, right? That's the magnetic field in this particular case. If you take the constant K outside, this becomes integral of X dA, and this integrated throughout the area. So basically you take a patch of area dA, okay, you find out its X coordinate, okay, and you do X dA for all the area elements, and that is what this integral represents, right? Now the integral of X dA, the area integral of that for some particular area, okay, this thing divided by the area of the loop, this is how the X coordinate of the centroid is defined. So if the centroid of this shape is somewhere over here, this term over here, this becomes the total area times the X coordinate of the centroid, okay? So it doesn't really matter what shape you choose, at the end it will always be the X coordinate of the centroid multiplied by the prefactor of the magnetic field. So I guess here it was B naught over X naught. So it will become B naught by X naught multiplied by the area of the loop multiplied by the X coordinate of the centroid. So in fact this is the only thing it depends on. And that's why for the circular loop and the square loop, the answer will turn out to be the same, because the area is going to be A square for both of them. So yeah, that's basically it for this problem. And also this particular problem about the dimensions, so I blundered this problem in the last video. So what happened was, so the factor gamma, it takes a value of half, right? So I by mistake crossed out the alpha equal to negative half, because the negative half occupied my mind there. So anyway, so for gamma equal to half, if you take X as G, you'll get B option, and if you take X as S, you'll get A option, okay? So in the last sentence, so they are saying X is either the universal gravitational constant G or the surface tension S. Now using the approximate variable, F can be expressed as, so they want us to choose the variable out of these two which is more appropriate in this situation, and that is quite straightforward. It's going to be the surface tension, right, which has a role to play in the frequency of oscillation of a bubble, right? Okay, so the answer should be option A, I guess. So if that's the logic that they wanted to use. So yeah, I guess that's it. Okay, so now let's discuss this problem. So this is from IPHO 2004. So in the question we have capacitors, a parallel plate capacitor, where the plates are circular and they are separated by a small distance d. The top plate is connected to a constant voltage source of potential V, and the bottom plate is grounded. A thin and small disk of mass m, radius of r, and thickness of t is placed on the center of the bottom plate. Okay, so its dimensions are much smaller in comparison to the dimension of the plate, and we have to assume the space between them is vacuum. The plates and the disc are made of perfect conductors, and inductance of the whole circuit can be neglected. Then we have to comment on the force between the plates before inserting the disc. Okay, so for option A, we can use the idea of electrostatic pressure. The force on any one of the plate is just going to be the electrostatic pressure, which is half epsilon naught V by d squared. This is the electric field in between the capacitor plates. This multiplied by the area of any of the plates, which is pi r squared. And the answer would be option A. Now when the disk is placed on the bottom plate, the charge Q on it is. Okay, so this is the diagram. So we have uniform electric fields that are flowing from the upper plate to the lower plate. Okay, and the dimension of the disk is very small in comparison to the plate. Okay, so we'll work with the assumption that the charge on this tiny conductor is not going to influence the external electric field too much. Okay, so with that we know that the electric field inside this conductor is going to be 0. So if we take a Gaussian box that looks something like this, let's say the normal area is A, then the electric flux on this top face is going to be the external electric field E multiplied by A, and this will be equal to the charge at the surface of this conductor. We can write it as sigma multiplied by A. Okay, so this would be sigma multiplied by A divided by epsilon naught. Okay, or simply speaking, just E equals sigma by epsilon naught. Now sigma, we can write it as the charge on the top face divided by pi r squared epsilon naught. Okay, so now under the assumption that the conductor does not influence the external field too much, this electric field E, we can just consider it as the electric field between the plates, which is going to be V by D. Okay, so we can substitute for E as V by D. And from here, the charge on the plate, so it's first of all going to be negative because if you observe, the flux is negative, right? So Q would be negative pi r square epsilon naught V divided by D. Okay, so option B will be wrong. To lift up the disk at rest, initially in the presence of a uniform gravitational field G perpendicular to the plates, the applied voltage has to be beyond a certain threshold voltage. Okay, so that's what we have to find now. Okay, so for that, first we'll find out the electrical force. In order to find the electrical force, we can still use the electrostatic pressure result, because we can just consider this conducting plate and the disk to be one single conductor, because they are both touching, right? Which means they are both at the same potential. So once again, if we want the force acting on this small disk, we can still use the electrostatic pressure result to write down the force on the disk. So it will be half epsilon naught V by D squared, and this thing multiplied by the area of the disk, which is pi r squared, pi small r squared. Okay, so this will be epsilon naught V square pi r squared divided by 2D squared. So this is approximately the electrical force that acts on the disk. And okay, so now for the threshold case, this will be just greater than mg, and this will be the answer for the threshold voltage. I guess what they were trying to do is write this as smaller and this as smaller as well, but okay, instead they wrote capital R by mistake. And okay, now in option D, they're saying when V is greater than Vt, the disk undergoes an up and down motion and eventually it comes to rest. So yeah, so when V is greater than the threshold voltage, the disk will start rising. Okay, and of course it will have some positive acceleration in the upward direction. So it will keep accelerating till it collides with the upper plate. Okay, and the IPHO problem, they gave the coefficient of restitution in this case. Okay, so we'll assume some energy to be lost in the collision. Yeah, so basically once it interacts with the upper plate, there will be a charge redistribution happening once again, and you guys can just check it using Gauss law once again. Here now the charge will become positive after coming into contact with the upper plate, and now it will be accelerated in the downward direction. So if you observe something, the disk is always being accelerated, both in the downward journey and in the upward journey. The only loss that is happening is during the collision. Right, during the collision, a fraction of the kinetic energy will be lost. But other than that, the disk will always keep on accelerating in between the two plates. So it won't eventually come to rest. So it will have an up-down motion, but it won't come to rest eventually. So option D would be wrong. So yeah, that's basically it for this question. Okay, so in this problem, we have a ball that is thrown from a tower of height. It has an initial speed of u0 in the horizontal direction. So for the resulting motion, the time taken for the ball to hit the ground for the first time after it is thrown is t1. So t1 is just square root of 2h by g, so which is 44.1 divided by 9.8. So this will cancel out with 2 and this will cancel out with 9. So t1 turns out to be 3 seconds. Okay. Now each time it hits the ground, its vertical velocity instantly reverses and decreases by alpha%. So if we zoom in this collision over here, if the collision velocity was v1, the reflected velocity will be v1, 1 minus alpha divided by 100, right? Now, if the motion continues for a long time, as shown in the figure, if the duration of the entire motion is 9 times t1 and the total distance traveled by the ball in the horizontal direction is d meters, then we have to find alpha plus d. Okay, so this time is going to be 3 seconds and this time is going to be 2 vy by g. Okay, so we can just add these well. And what is v1? v1 is going to be root 2gh. So this is the initial vertical velocity. Okay, so now we can just equate the times. So the time taken to go from here to here will be 3 seconds. So 3 seconds plus the time taken for this projectile is 2 v1 by g times 1 minus alpha by 100. So now the next term will be just 1 minus alpha by 100 multiplied again. So this is just going to be a geometric progression now. And on the right side, we'll have the total time 9 t1, which is 27 seconds. Now v1 by g is going to be square root 2h by g, right? So this is just 3 seconds. So 2 v1 by g will be 6 seconds. And for the gp, we can use the sum formula. So it will be 1 minus alpha by 100 divided by 1 minus the common ratio. So this should be equal to 24. and you cancel this thing out. So the denominator is just alpha by 100, and from here alpha by 100 is 1 by 5, or alpha is 20. Okay, now for the total horizontal distance, we can multiply time of flight, which is 27 seconds, or with the horizontal speed, which is 10 meter per second. So this will give you the answer as 270 meters. Okay, so now they wanted the sum of these two, which is 270 plus 20, which would be 290. So now moving on to question 10. So here we have, there's a similar problem like this and 200 more puzzling problems. So in this question, we have a metallic sphere whose radius is r, and it's cut into two identical hemispheres, and the cut surface is coated with a thin insulating layer of thickness d, which is negligible in comparison to the radii of the sphere. And the two parts are then put back together. One of the hemispheres is then given a positive charge of plus q, while the other one remains neutral. Okay, so then we have to comment on the electrostatic force between the two hemispheres. So let's say this is the insulating layer, okay, and these two are the half hemispheres. Now one of them, let's say the left plate, is given a total charge of q, and the right half is still neutral. So firstly, this middle section over here of the insulating layer, this part we can consider it as a parallel plate capacitor, because the two circular surfaces, they are very close to each other in comparison to the radii of the sphere. So this is basically a parallel plate capacitor. So on this left hemisphere, there are going to be charges on the circular surface. So let's say it is some q, and the rest of the charge will be on the outer surface. There won't be any charges inside the volume. So on the outer surface, we'll have a charge of capital Q minus small q. So let's say in this surface, we have a charge of q. Okay, so then the charge on this particular surface of the other conductor, this should be negative q. So this is just the stuff we discussed in capacitors, right? So this is mainly to ensure that if you take a Gaussian surface, something like this, the q enclosed would be 0, so there won't be any electric fields here. Okay, just due to this plus q and minus q. Okay, so on the hemisphere, we'll have a charge of capital Q minus q, and on this hemisphere, we'll have a charge of q. Okay, so now for the second, let's say the left hemisphere is at some potential v. Okay, then the thing is, every point on the left hemisphere will be at the same potential, right? So there will be an electric field due to this capacitor in this insulating region, right? So that electric field is just going to be q by a epsilon naught, where a is pi r squared. But the thing is, the thickness d is extremely tiny. So the potential drop, that is q by a epsilon naught multiplied by d, this is actually very tiny. So the thing is, we can almost approximately say that if the potential of the left hemisphere is v, then the potential of the right hemisphere is also v. So basically what that means is that we can consider the sphere as one single sphere itself, which is at the same potential. And if you observe, the total charge that is distributed on the outer sphere is capital Q. Now this just represents our original case where we have a conducting sphere and we distribute a charge plus q, and we give it a charge of plus q. So we know that the charge distribution in this particular case is a uniform charge distribution, sigma, where it is equal to q by 4 pi r squared. So that would be exactly the same in this case as well, because the conditions are the same. So even in this case, we have a sphere that is at a constant potential of v, and we have a total charge of capital Q distributed on it. And this problem is also very similar, or basically the same as the other problem. So what will happen is that the q minus q and the q, they would mutually arrange themselves in such a way that we obtain a uniform charge distribution in the outer surface. Okay, or basically we can say that the sigma of the charge distribution on the hemispherical side is just going to be q divided by 4 pi r squared. Okay, which means on one half we'll have q by 2, and on the other half also we'll have q by 2. Now in the puzzling problem example, they took the surface to be somewhere over here, right? So there you'll have to find the area, okay, and then do sigma multiplied by area to find the charge on one surface. Okay, so here it's simple because the insulating part is at the middle. So on one half we'll have q by 2, and on the other half also we'll have q by 2 charge distribution. Okay, so now let's talk about the forces acting on one of the hemisphere. Okay, so first we'll use the electrostatic pressure idea. So the electrostatic pressure at the surface is sigma square by 2 epsilon naught, right? And that we can multiply it with the projected area of this hemisphere. And this will give us the repulsion force by the surface charges present on the other hemisphere. The F1 is just the force due to the surface charges present on the other hemisphere. Okay, and yeah, this q will also be capital Q by 2, and this will also be negative q by 2. Okay, so yeah, F1, this is the electrostatic pressure term, So this would be sigma square by 2 epsilon naught multiplied by the projected area of any hemisphere in the vertical plane. So the projected area of this hemisphere in this plane is pi r squared. So this will be F1. And the second force, and secondly, we'll have an attraction force between these two surfaces of the spheres. Okay, and for this we can use the capacitor result. So the F2 force, which is towards the right, and F1 was towards the left. So F2 would be the, so for F2 we can just use the result Q squared by 2a epsilon naught. So this was the force of attraction between two plates of a parallel plate capacitor, right? So this is going to be Q squared divided by 8 epsilon naught pi r squared, right? Because the area of this plate is pi r squared. Okay, so now sigma we can write it as Q by 4 pi r squared. So this becomes Q squared by 32 pi epsilon naught r squared. Okay, so they want the answer in terms of kq square by r squared. So this we can write it as kq squared by 8r squared, and this we can write it as kq squared by 2r squared. So the attraction force is actually stronger. So the net force is going to be kq square by 2r minus kq square by 8r squared, and this would be 3 by 8 kq square by r squared. So the answer for n is 8 by 3, which would be 2.67. Okay, so yeah, I guess that's the answer for this. Now let's move to the next one. So in this problem we have a wave pulse, which is a rectangular wave pulse whose width is 0.4 and it is traveling to the right on a taut string of linear mass density of mu1. The string is now attached to another taut string of linear mass density mu2. The tension in both the strings is same. So if the transmitted wave pulse has a width of 0.6 centimeters, the ratio mu1. So now the change in the width is mainly associated with the difference in the traveling speeds of the waves in these two strings. Like for example, let's say the wave, when the right end of the wave pulse reaches the interface, okay, the left end is at a distance of 0.4 centimeters, the interface, right? If the travel speed in this left string is actually v1, the left end of the wave pulse, it will take another time t, which is equal to distance 0.4 divided by v1 to reach the interface. Okay, so because it's traveling with a speed of v, so what that means is it will take, in order to cover a distance of 0.4, it will take a time of 0.4 by v1. But meanwhile, in this particular time, the disturbance of the front of the pulse has entered the second string already, and there it is traveling with a different speed, and in fact it is greater. So as the speed is greater in this particular medium, in this particular time of 0.4 by v1, it covers a larger distance. So the amplitudes are going to change a bit as well, but we only need a rough diagram. The front end of the wave, it covered a distance of 0.6 centimeters. So what that means is, in a time of 0.4 divided by v1 seconds, what is the distance traveled by the front end? It will be v2 multiplied by 0.4 by v1, and this is given to be 0.6. So I guess that's it. So v2 by v1 equals 3 by 2. Now the velocity is inversely proportional to the square root of the linear mass density. So this we can write it as square root. So this we can write as square root of mu1 by mu2, which implies mu1 by mu2 is 9 by 4. Okay, so this is going to be 2.25. So now moving on to problem 12. So in this problem, we have a door that is opened with a very high angular velocity. The high angular velocity about its hinge. Over a very short period of time, its angular velocity increases to 9 radians per second due to the force applied at the ends opposite from the hinge. So the angular acceleration in this case is considerably high. The door can be considered to be a uniform rod of length L and mass M. The hinge is located at one end of the rod. If the distance from the hinge of the door to the point where the door is most likely to break is x equals L by n. The thing here is, guys, I guess what they wanted you to analyze is the bending moment. Okay, and it's not the centrifugal force that they wanted you to analyze, and it's not the shear stress also. It's probably the bending moment that they wanted you to analyze. And I guess for they should actually mention that. So like something like find the point where the bending moment is maximum, okay, or something like that. Yeah, otherwise this question is confusing, right? Because which effect do you actually consider? Do you consider the centrifugal effects? Because if you consider the centrifugal effects, the maximum tension or the tensile force along the rod will be at x equal to 0, right? Which would make this question absurd. And the maximum shear force is actually, I guess close to the point of application of this force F. So which is also not an L by n type of an answer, right? So it would be n equal to 1 in that case. So yeah, they're probably talking about the point where the bending moment is maximum. Okay, and that's what they want you to analyze. Yeah, let's look at a few pictures first. So again, this is related to what bending moment actually is. So consider this beam that is placed on two supports, something like this, and we are applying a load. Okay, so this W just means it's just a load that is applied, and as a result, it's intuitive that the beam will actually bend, right? So here, what happens is that the fibers present on the top part, they will actually get compressed. So the fibers of the rod that are present on the upper surface, they will actually get compressed, and the fibers present on the lower part will actually elongate. And if you observe, they have marked a certain axis over here called the neutral axis or the neutral plane. So basically this is basically that axis whose length doesn't change. Okay, so we don't have to get into too much complications, but now because of this bending, what will happen is that the points above the neutral plane, these are the points that get compressed. Okay, so if you take any section over here of the rod, then the points on the upper half will actually feel a compression force, and the point on the lower half will feel a tensile force, which means it's pulling in nature. So that's what we observe from this diagram as well. Here there was some kind of a bending force that was applied like this. Now, because the top surface is being compressed, the tension forces are compressing in nature, and beyond a certain point, which is called the neutral axis, which is kind of irrelevant right now, the tensile force actually changes its direction. The net force obviously still remains zero because it's in equilibrium, but this constitutes a non-zero moment if you observe, right, which is in the counterclockwise sense as viewed from this side, and this is the moment that tries to bend the beam, okay, at this particular section. So basically, if you want to find the bending moment, let's say at this section, all you have to do is draw an FBD of the left part, okay, while including the forces at this section. So you will include a shear force in this particular case. Let's say it is V. Now, okay, so now this is how the shear forces will look. The forces are going to be parallel to the area, and so if this is the section, then the shear force will include it something like this, up or down, doesn't matter. And then we'll put a bending moment, which is just a torque, okay, trying to bend that section or the rod, which is the resultant of these forces, okay. Once again, you can apply it clockwise or anti-clockwise. If it's wrong, the answer will just become negative. So that's just like a brief idea of what bending moment is. I'll link a video in the description for you guys to get more intuition into what bending moment is. Okay, so yeah, now coming to this problem, so let's begin by marking the hinge force in the y direction. So let's just say the hinge force is some Fy. Of course there will be an Fx as well, but we'll find it if we need it. So the angular acceleration is pretty easy is just going to be F into L divided by the moment of inertia about the hinge. This is FL divided by ML square by 3. So from here, F is nothing but 3 ml alpha divided by 3. So now what's the acceleration of the center of mass? It will be L by 2 alpha, right? So now we can apply F equal to ma in the y direction. So we get Fy plus F, which is ml alpha by 3, equals mass times the acceleration of the center of mass. So from here, Fy turns out to be ml alpha by 6. Okay, so the pivot applies a y direction force of ml alpha by 6. Okay, so now the thing is, we can consider this section over here, which they have shown at a distance of x. Okay, we can draw its FBD. So the pivot applies a y direction force of Fy. There's going to be an x direction force as well, but I'm ignoring that for now. The length of this part is x, I'm considering. Now on the sectioned part, we'll have a shear force, okay, which let's just take it as V. I'm ignoring the force in the x direction, but there will be a tension along the rod, of course. And let's just say the bending moment is some m in the clockwise direction. Okay, and these are all I'm assuming, and these are all randomly assumed. Okay, so now we can apply once again tau equal to I alpha about the hinge O. The torque due to the shear force will be V multiplied by X, and the bending moment is bending it in the clockwise sense. So we'll put a negative M sign because the V is trying to bend it in the counterclockwise sense, right? Now this is equal to the moment of inertia about O, which would be mx by L. This is the mass of this x part, the length squared divided by 3. This is the moment of inertia multiplied by alpha. Okay, so now and this acceleration of the center is just going to be x by 2 alpha. So we can apply Fy, which is equal to ml alpha by 6 plus V is equal to mx by L multiplied by x alpha by 2. So from here, V turns out to be m alpha x square by 2L minus ml alpha by 6. Okay, so now we have the shear force as a function of, okay, so now here if you observe the shear force, it increases quadratically with x. Okay, so the maximum shear force will be at x equal to L. Anyway, so now all we have to do is substitute V into this expression and solve for m. Okay, so this is what the bending moment turns out to be. I realized that I took the same symbol as the mass, but the maximum, so the maxima, we can just figure it out using differentiating. So we'll just say dm over dx and we'll set it equal to 0. So we'll get m alpha x squared by 2l minus m alpha l over 6. From here, x squared turns out to be l squared by 3, or x equals l by root 3. So this is the point where the bending moment is maximum. So that point is going to exhibit the highest amount of bending stress, and that is probably the phenomena they wanted you to analyze. Okay, yeah, in this situation n would be 1.73 because n is just root 3. Okay guys, so that was it for this video. If you have any doubts, you can ask below. If you enjoyed, make sure to like, share and subscribe. That's it. Thanks for watching.